Our last video by taking a look at some pictures, some graphs of how closely our Taylor polynomials were approximating cosine of x. And we saw in some cases it was a good estimate, in other cases it was not a good estimate. As we added more and more terms, it became a better and better estimate that applied over a larger and larger interval. But it would be good to be able to make that precise. It would be nice for us to be able to, without drawing a picture, to just know how good our estimate is. And this should make sense. Like, if I tell you some measurement is 10 inches, approximately speaking, that's in some sense meaningless without telling you how much the error could be. So if I tell you it's 10 inches and I could be off by at most 0.2 inches, that's a pretty good estimate. That it's somewhere between 9.8 and 10.2 inches. It tells you a lot. But if I tell you a measurement is 10 inches and I could be off by up to 7 inches, well, then it could be anywhere from 3 to 17 inches. That's a pretty big error. In some sense that estimate is close to meaningless. And so it would be nice for us to have some way to meaningfully estimate and tell you how big the error is, or give an upper bound on how big the error can be for our Taylor polynomials. And that's what this theorem that you've probably been looking at, that's what this theorem does. So theorem 2, the error bound, it tells you how big the error is going to be. So we assume that the m plus first derivative of our function f exists and is continuous, and that k be some number such that the absolute value of the m plus first derivative evaluated at u is less than or equal to k for all u between a and x, where this a, this is the center of your Taylor series, and this x, this is where you're going to be estimating your function using I said Taylor series, I meant Taylor polynomial. We'll be talking about Taylor polynomials in the next section. This is where we're going to be estimating our function using our Taylor polynomial. Then, the absolute value of f of x minus t sub n of x, so this is the error. This is the actual value of our function at x. This is our estimate for the value of our function x. This absolute value is less than or equal to k, this k up here, times the absolute value of x minus a raised to the m plus first power divided by m plus 1 factorial, where t sub n is the nth Taylor polynomial. Okay, so this tells us how close we are. Let's actually apply this in some situations to see how this works in practice. So let's apply the error bound to estimate how big is the error for natural log of 1.2 minus t sub 3 of 1.2, where t sub 3 is the third Taylor polynomial for f of x is equal to natural log of x at a is equal to 1. So I chose this problem. The textbook chose this problem. This is something that we've already dealt with here. So let's see. What do we have to do? All our derivatives exist and are continuous. That's good. Let k be a number such that so here we are working with n is equal to 3. So we are looking for absolute value of f of the fourth derivative of f evaluated u. We want this to be less than or equal to k for all u between a is 1 and x is 1.2. Okay, what is the fourth derivative of u? We've got that it is going to be minus 6 times u to the minus 4th. Minus 6 times u to the minus 4th. The absolute value of that is going to be 6 u to the minus 4th. U is between 1 and 2, so we don't have to worry about absolute value or anything there. And note that this is a decreasing function. So as u gets bigger and bigger and bigger, 6 over u to the 4th gets smaller and smaller. So the maximum here is when u is equal to 1, and that max value is 6 divided by 1 to the 4th is 6. So we're going to take k to be 6. So now at this point, we are ready to use our error bound. So we've got that k in here. So what does this say? The absolute value of f of x, I'm just going to recopy this, and then we will plop in things as appropriate. Okay, so f of x is going to be so here x is 1.2, natural log of 1.2 minus t sub 3 of 1.2. This is what we are aiming for in the first place. So this is less than or equal to k. Our value of k that we just had was 6 times the absolute value of 1.2 minus 1 raised to the n plus 1. N was 3, so n plus 1 is 4, divided by n plus 1 for factorial. Okay, so here's what we have over here. If we crunch, this is about equal to 0.0004. And so that is a pretty darn good approximation here. And so if we were to do natural log of 1.2 is about 0.182667. T sub 3 of 1.2, where, just to remind you, T sub 3, that is something that we would have calculated out before. So we've got the general formula here for t sub n of x, so we plug in t sub 3, and we stop there. So t sub 3 of 1.2 is about 0.182322, and so the error here is, this is about 0.00035, which sure enough is a little bit less than 0.0004. And so the textbook has a picture of this, and so you can see here the red line is log of x, well, not line, but curve. The blue curve is t3 of x, and you can see that near 1, and in fact still near 1.2, you really can't tell a difference between those two curves. So it makes sense that we can say those are really close to each other.